You step into a building that never truly rests. Before you even see the furnace, you feel it. A low, constant vibration travels through the ground. Steady, mechanical, like something enormous breathing beneath your feet. The air is heavy, dry, and hot enough to sting with every inhale. Then you see it. A towering structure of steel and brick, rising like a cathedral built for fire. Pipes coil around it, valves hiss, flames flicker in controlled bursts, and somewhere inside, hidden behind layers of refractory lining, iron is being pushed past the limits of solidity, heated until it flows like liquid light. But here's the part most people never realize. The most dangerous moment inside a blast furnace isn't when it's running. It's when someone tries to stop it. Because once this system is alive, it depends on that heat to survive, and removing it can be just as destructive as letting it burn. Step closer. The furnace dominates everything around it, nearly 30 meters in height in some cases. It consumes raw materials from the top, iron ore, coke, and limestone layer by layer. From below, blasts of superheated air surge upward, driving chemical reactions that strip oxygen from the ore and leave behind molten iron. It's not quiet. A deep roar fills the space, air forced in at extreme temperatures, gas rushing through ducts overhead, the occasional metallic groan as the structure shifts under thermal stress. It's a sound you don't just hear, you feel it in your chest. The heat is constant, not a sudden wave, but a pressure that builds the longer you stand there. It settles into your skin, dries your throat, slows your thoughts. You wouldn't last long here. The men who worked these furnaces stayed for 12 hours at a time, and the furnace never stopped for them. At the height of the industrial boom, this wasn't seen as dangerous. It was seen as necessary. Blast furnaces were symbols of progress, machines that turned raw earth into iron, iron into steel, and steel into cities. Bridges, railways, skyscrapers, all of it began here. And for that process to work, the furnace had to remain in constant operation, because inside, everything depended on heat. The internal lining, made from specialized refractory brick, expanded under extreme temperatures. Over time, it settled into a delicate equilibrium. But if the furnace cooled too quickly, that balance would collapse. The bricks would contract, cracks would form, hidden damage would spread through the structure. Restarting wasn't just difficult, it could mean rebuilding the entire interior. So, operators avoided shutdowns whenever possible, even when something didn't feel right. And that's where the real problem began. Because what looked stable from the outside was anything but. Inside the furnace, opposing forces never stopped moving. Materials descended slowly under gravity, while hot gases surged upward under pressure. Chemical reactions released heat, altered density, shifted flow patterns. It was a system in constant motion, and no one could see directly inside it. There were gauges, indicators, experience passed down from older workers, but there was no complete picture. So, the men relied on what they could observe. Subtle changes in flame color, unusual vibrations, the way heat radiated from specific areas. They didn't control the furnace completely. They interpreted it. And sometimes, they misread the signs. If you enjoy these deep dives into real engineering stories, consider subscribing. It helps me keep making videos like this. Now, imagine this. You're halfway through your shift. Your clothes soaked through. Your hands rough from handling tools heated by the surrounding air. Every movement feels slower than it should. At first, it feels like exhaustion. Then, something shifts. A dull headache begins to form. Your vision tightens slightly at the edges. You lose track of small details, where you placed something, what you were about to do next. It's subtle, easy to ignore. But it isn't fatigue. It's the air. Blast furnace gas, produced as a byproduct of the process, moves constantly through the system. Under normal conditions, it's captured and reused. But early plants weren't perfectly sealed. Leaks happened. And the gas contained something dangerous: carbon monoxide. Colorless, odorless, impossible to detect without instruments these workers didn't have. When it accumulated, it didn't cause panic. It caused confusion, disorientation, and then collapse. Many workers never realized what was happening until they were already unable to react. And in some cases, the men who tried to help them were overcome the same way. But even that wasn't the most violent threat, because the furnace carried another danger, one that built slowly, silently over time. Wear. Inside the structure, the refractory lining was constantly exposed to molten iron and slag. Day after day, year after year, that surface eroded. Not evenly. Some areas thinned faster than others. Heat concentrated in weak spots. Stress increased in places no one could directly inspect. From the outside, the signs were easy to miss. A slight distortion in the steel shell, a new vibration underfoot, a patch of heat that felt stronger than it used to. Each one small, each one explainable. But together, they pointed to something much more serious, a structure approaching its limits. This is where everything starts to go wrong, because stopping the furnace to investigate those signs wasn't a simple decision. Shutting it down meant risking internal damage. It meant lost production, lost revenue, and potentially months of downtime. So instead, crews adapted. They patched visible issues, reinforced outer sections, adjusted operations slightly. They kept it running. One more day, one more shift, hoping the system would hold. Until it didn't. When failure came, it didn't build gradually. It arrived all at once. A breakout. Somewhere inside the furnace, the lining gives way. Molten iron, heated to temperatures above 1500 degrees Celsius, finds a path through the weakened structure. And once it breaks through, it doesn't stop. It surges. A dense, glowing flow of liquid metal bursts into the open, spreading across the floor. It burns through steel supports, ignites debris, and radiates heat intense enough to warp nearby structures. There's no time to analyze, no time to plan, only time to react. You run, because distance is the only protection that exists in that moment. And here's what makes it more dangerous. There isn't always a clear warning. No alarm system, no automated shutdown. Just a sudden shift from routine operation to uncontrolled release. Night shifts were especially vulnerable. Fewer supervisors, reduced visibility, slower reaction times from fatigue. Workers relied on instinct, routes memorized through repetition. They knew where to go, how to move, what to avoid. Because when something went wrong, hesitation could cost everything. And yet, even after an event like that, the furnace wasn't abandoned. It was repaired, relined, put back into operation, because the system depended on it. Now, consider this. In many cases, shutting the furnace down intentionally was seen as more dangerous than continuing to operate it. Cooling had to be carefully controlled over long periods. If done improperly, internal cracking could render the entire structure unusable. Restarting introduced its own risks: uneven heating, structural stress, unpredictable reactions. Some furnaces never returned to service after a shutdown. The cost, financial and operational, was enormous. So operators faced a constant calculation: continue running with known risks, or stop and face uncertain consequences. Neither option was safe. Behind every decision were people. Workers who understood the danger, even if they couldn't fully measure it. Men who learned to read subtle changes in the system, who adapted to conditions that would overwhelm most others within minutes. They weren't careless. They were operating within limits set by both technology and demand. Because the demand never stopped. As the industry grew, so did the furnaces: larger structures, greater output, higher internal pressures, more material moving through the system at any given time. From the outside, it looked like progress, and in many ways it was. But increasing scale introduced a new kind of risk. Because the larger the furnace, the more energy it contained. And when something went wrong, that energy had to go somewhere. Failures became less frequent, but more severe. So why not redesign everything completely? Why not eliminate the danger? Because the danger wasn't a flaw in the system, it was part of the system. A blast furnace operates by maintaining extreme conditions: heat, pressure, chemical imbalance. Remove those, and the process stops working. Control could be improved, but it could never be absolute. Over time, changes were made. Better refractory materials extended furnace life. Ventilation systems improved air quality. Monitoring became more precise. Accidents decreased. Understanding increased. But the fundamental reality remained. This was controlled intensity, not controlled safety. And that's the part that still matters today. Because modern industry has advanced far beyond these early systems, but the principle hasn't changed. Some machines don't become safe, they become manageable. So when you look at steel, buildings, bridges, infrastructure, remember what it took to produce it. Environments where heat reshaped materials and tested human limits. Systems that demanded constant tension, constant adjustment, constant risk. And a machine that once ignited could not simply be turned off without consequence. Because the furnace never responded to intention, only to physics. Heat, pressure, time. And when those forces drifted out of balance, it didn't fail quietly. It reminded everyone how fragile control really was.